In contemporary deep learning, there's a significant emphasis on crafting the right objective functions to ensure that the model's predictions closely align with actual outcomes. Additionally, there's a need to design effective structures that can gather sufficient information for accurate predictions. However, many current approaches overlook the critical aspect of how input data is perceived and utilized during this process. This research introduces new methodologies that focus on programmable gradient information, enabling models to learn more effectively based on what the users want to achieve with their predictions. By addressing these gaps, the study aims to enhance the performance of deep learning systems. Method. Data loss in deep networks. The initial discussion emphasizes a crucial aspect of deep learning, particularly how data undergoes a systematic process of layer-by-layer feature extraction and spatial transformation. In simpler terms, as information passes through various layers of a neural network, significant portions of it may become lost or degraded. This can occur because each layer filters and transforms the input data, potentially omitting critical details necessary for accurate analysis. The concept of data loss is explored further with a focus on two primary challenges: information bottleneck and reversible functions. The information bottleneck refers to the phenomenon where relevant data gets compressed too much, leading to a loss of important characteristics needed for effective model performance. This can hinder the model's ability to generate accurate predictions or classifications based on the input data. Reversible functions are introduced next, spotlighting their importance within the context of deep networks. These functions allow certain transformations to be undone, preserving some of the original information despite the processing that occurs. The interplay between these reversible functions and information bottlenecks sets the stage for further exploration of how deep networks handle and reconstitute data. To address these issues, the authors propose an innovative solution known as programmable gradient information, PGI. This concept aims to mitigate the challenges posed by the aforementioned data loss, offering a potential avenue to enhance the robustness of deep learning models. The details surrounding PGI will likely encompass how it functions and its intended impact on maintaining information throughout the network's operation. By framing the discussion around these key ideas, the paper not only raises awareness about common pitfalls in deep learning systems, but also proposes direction for further investigation into methods that could sustain data integrity across complex transformations. The stage is set for the subsequent sections to delve deeper into the specifics of PGI, detailing its implementation and effectiveness within the broader context of deep learning methodologies. This exploration signifies an important shift in how data may be preserved during the intricate processes within deep networks, encouraging further analysis and potential advancements in the field. In the second part of the method section, the focus shifts towards the implementation of a new lightweight network architecture, which plays a critical role in enhancing the model's efficiency and effectiveness. Input calculation and objective functions. Here, the text introduces the concept of PGI, which stands for a specific mechanism or framework used within the model. PGI is designed to supply comprehensive input data pertinent to the task at hand. This complete dataset is crucial for computing the objective function, essentially a mathematical representation of the task's goals. By ensuring that the input information is thorough, PGI facilitates the reliable acquisition of gradient information. In simpler terms, gradients are like directional indicators that help the model figure out how to adjust its parameters, referred to as weights, optimally to minimize errors during training. Efficient network architecture. Next, the text transitions into discussing the Generalized Efficient Layer Aggregation Network, GELN. This innovative architecture is designed with lightweight principles in mind, which means it can operate effectively without requiring excessive computational resources. This is particularly useful in scenarios where processing power or memory may be limited. GELN likely incorporates features that aggregate various layers of data efficiently, allowing the model to draw on multiple sources of information simultaneously without overwhelming the system. The synthesis of PGI and GELN provides a robust framework for improving the model's capacity to learn from complex data. By navigating through various objectives simultaneously and ensuring that reliable feedback is available for updates, the architecture can maintain high performance under various conditions. In conclusion, These efforts in optimizing the model through procedural innovation set a strong foundation leading into the experiment section. The methodologies detailed here, ranging from input calculations to the implementation of a streamlined architecture, suggests that the forthcoming experiments will rigorously assess the effectiveness and efficiency of these advancements in real-world scenarios. The application of PGI and GELIN clearly positions the research at the cutting edge, ready to push the boundaries of what's achievable in machine learning tasks. In this section, entitled Experiments, the authors describe the experimental setup designed to assess the performance of GELIN, a model based on gradient path planning. The architecture of GELIN is noted to enhance efficiency by leveraging the advantages of parameter grouping interaction, PGI, implying that it can gain superior results while maintaining a lightweight structure. The experiments utilized the widely recognized MS-COCO dataset, which is pivotal for object detection tasks. This choice underscores the relevance and applicability of the findings in real-world scenarios, as MS-COCO contains diverse images with complex structures, facilitating comprehensive testing of the proposed models. The results indicate that GELIN predominantly employs conventional convolution operators. This methodology stands as a crucial factor leading to improved parameter utilization compared to existing state-of-the-art approaches. The significance of this finding is twofold. First, it highlights the model's efficiency, meaning it can achieve higher accuracy with fewer resources. Second, it signals a potential shift in method preference from more complex models to simpler, yet effectively optimized architectures. Accompanying the results are detailed comparison tables that illustrate the performance metrics across different models tested on the MS-COCO dataset. These tables serve as a visual representation of the outlined performance metrics, making it easier to assess how GELIN stacks against other competing models. The performance metrics typically include precision, recall, and mean average precision, MAP, which are standard in object detection tasks. Such comparative analysis not only grounds the experimental findings in quantitative terms, but also provides a clear narrative on the strengths of GELIN, particularly in lightweight model settings. This thorough examination of both the experimental design and the results serves to delineate the advantages of the proposed approach, paving the way for a deeper understanding of its implications as we transition towards the paper's concluding remarks. Through clear metrics and idea-driven discussions, the subsequent sections will summarize key insights and future directions drawn from these empirical findings. In the conclusion section, the research underscores the effectiveness of advanced art methods centered on depth-wise convolution. A noteworthy outcome of this study is the introduction of the PGI, Performance Gain Indicator, which demonstrates versatility across different model sizes, from lightweight frameworks to large architectures. The findings reveal that models trained from scratch using PGI can outperform current state-of-the-art competitors that rely on extensive pre-training with large datasets. This breakthrough is visually supported by comparison results displayed in Figure 1. The implications of this research are profound, suggesting a shift in how models can be developed, emphasizing efficiency without sacrificing performance. Overall, the paper concludes that these insights could reshape future workflows in model training within the field.